Alright then, now the next section is on transducers, and so we'll go through these. This will talk about probably as much as you need to know about transducers to get through the SPI exam. So what is a transducer? This is a question comes up, and the answer is any device which converts one form of energy to another. So an ultrasound transducer is a specific type of transducer, and it has two functions, so it's what we call bidirectional transducer. It can convert electrical energy into sound, and then the other direction it can convert sound energy into electricity. So that means it's bidirectional. And ultrasound probes are bidirectional, and you could also think of a pendulum as something that's bidirectional because it churns gravitational energy or potential energy into kinetic energy and back. So that's one type. Other types of non-bidirectional transducers are things like a torch, which you could light on fire and burn the chemicals on it to produce light and heat. Or a light bulb, which is an electrical energy is turned into light energy and heat also. And something like a rubber band, which can turn potential energy into kinetic energy. So those are all examples of different types of transducers, and I'm sure you can think of many other examples yourself. So what does a transducer utilize in order to do this transfer of energy? And what it uses is known as the piezoelectric effect, which is a property of materials that when a voltage is applied to them, they will mechanically deform. These are interesting little crystals that naturally occur. And they change shape when the voltage is applied. And some types of piezoelectric materials, such as the crystals we use in ultrasound transducers, have what's known as the inverse piezoelectric effect, and that is when the shape is changed, then a voltage is created. So piezoelectric materials are simply materials that convert, for our purposes, are materials that convert sound into electricity. And there's some natural occurring types of piezoelectrics out there. Some are like quartz is a natural piezoelectric, and tourmaline, another mineral that is found in nature, are also piezoelectric. There's a lot of man-made types of piezoelectric materials, and the one we're going to be most interested in is the lead zirconate titanate, or what we call PZT, P for lead, zirconate, Z, and T for titanate. This is the most common one that we study in ultrasound and is becoming less used in today's transducers. Now we're using more of the polymer piezoelectric materials, but certainly PZT is the one we study. And so there's some other types of man-made piezoelectrics. As I said, the polymer piezoelectrics, these are polyvinyl type piezos. They're really becoming the most used in actual manufacture today. And then the silicon micro-machining ultrasound technology, also known as MUTS, is a very popular type of piezoelectric being used today. So let's look at the transducer itself. So we have here a diagram of really what is the simplest transducer we could pretty much make. And it consists of a piezoelectric element made of the crystal. This would be a single crystal element that is on this simple transducer. It has backing material behind the transducer, behind the crystal, behind the element, and this damping material or backing material, it's known as both, is able to deaden the movement of the transducer element. And there's, in front of the element, there is a matching layer, and this matching layer helps to get sound to move from the element into the human body. The matching layer is required due to the difference in impedances between the body and the transducer element. We'll go more into that in a little bit. And then the next is the casing that is, it holds everything together into one piece. And then most transducers, of course, have a strain relief and then the cord, the cabling. In the cabling, of course, there's many smaller cables within that. So when we look at a transducer, this is the most simple one that we can have. Now, most of the transducers we use today are phased array transducers. And when I say array, what I mean is that there are many elements within the transducer that are lined up one after the other in a single line or array. And so these array transducers, the simplest ones, have a width, a crystal across the width, and then many crystals along the length of them. Or I guess you could say this would be the width or the length, and then this would be the width of it, whichever. But the main point here is that there are multiple small crystals that make up a phased array transducer. So array transducers are very similar to the single crystal transducers, except we have many more pieces of crystal in them. That's really the main difference. And so we have our piezoelectric materials. Again, we have our backing materials or damping materials. There's a case, and then there's the strain relief, the matching layer, and the cabling. So this is the same as that simple transducer we were looking at, but the main difference is the way the piezoelectric material is lined up on it. So let's talk about the matching layer again. The matching layers are layers that are required because of the difference of impedances that are reflected at boundaries. The impedance of piezoelectric material is about 20 times that of the skin, and if you had no matching layer, about 82% would be immediately reflected back into the transducer and then absorbed by the backing layer. And so we'd get very little to propagate into the tissues, and then of course when it was reflected back from echoes within the body, it wouldn't cross the boundary to get back to the transducer to make a display. So we have to have a matching layer, and the matching layer will always have an impedance somewhere between the value of the impedance of the PZT layer and the value of the impedance of the skin. And you could also think of your gel that you utilize as another matching layer. So in this case, there's always going to be at least 2 matching layers whenever we use an ultrasound probe, the actual matching layer on the transducer itself and the gel. But the truth is that the matching layers on the transducer are generally made up of 2 or 3 matching layers within themselves. So we'll always see that the matching layers, the impedance differences between each matching layer is the impedance at the PZT is always the greatest, and the skin is always the least amount of impedance. And so you see these layers of matching impedance differences, the piezoelectric, the matching layer, the gel, and the skin in that order. So the impedance then allows more of the sound to transfer into the body and back from the body back to the transducer. So there is a geometric consideration to be made with matching layers, and that is that their size has to be a quarter wavelength of whatever the wavelength of the sound is in the crystal. The thickness of the matching layer is always a quarter wavelength. And this, again, as I said, has to do with geometric reasons that we don't really need to go into. But it reduces the reflection back to the transducer by having it that thick. The PZT crystal thickness is always going to be 1/2 a wavelength of the size of the sound wave in the crystal. So we have two thicknesses we need to be concerned about. Matching layers are a quarter wavelength in thickness, and PZT crystals themselves are a half wavelength in thickness. And again, this wavelength comes from the frequency and the speed of sound in the crystal itself, not the speed of sound in the body. The backing layer is a very important part of the transducer, and what it does is it allows us to strike our transducer element with an electrical voltage and then have it almost immediately stop ringing. If you had a bell and you strike it, it's going to ring for a long time, so that's not good. We want to have our transducer stop ringing almost immediately. We want one or two waves out of the pulse and then have it stop. This provides better axial resolution, because the shorter your spatial pulse length, the better your axial resolution. Some of the properties that backing material will have are high acoustic absorption, so they absorb a lot of the sound that's created by the crystal. And you want to have a backing layer with a very similar impedance to the PZT crystal. Again, that allows the sound to go into the backing layer and not to remain in the crystal. If you're using a backing material, you get decreased sensitivity because the backing material absorbs a lot of the sound that hits the transducer, but you get what's known as a wide bandwidth with your sound, which is a lot of frequencies to use, and you get something called a low quality factor. And all imaging transducers rely on a low quality factor in order to be useful. So let's talk about what bandwidth is. So bandwidth is the range of frequencies over which the crystal operates. So when you strike the crystal with an electrical pulse, it'll create many frequencies, though the center frequency will always be the strongest. And it's like striking a bell. You'll always hear a particular tone from a bell, but you'll also hear tones above and below at different frequencies with the bell also. When we measure the useful frequencies from lowest to highest, we call that the bandwidth. And for most transducers, what we do is we look at the sensitivity of the transducer at the central frequency, and anything that is within 3 decibels less than the main sensitivity at the center frequency is considered a useful frequency. So if we drop down 3 decibels, we look at where this 3 decibel line crosses our bandwidth, and we can then say that this is the bandwidth of this particular crystal. It goes from whatever frequency 1 is up to whatever frequency 2 is, with its strongest ability at the center frequency, frequency sub-0 here. So we always say that the frequency of our probe is whatever the center frequency is, but remember that even though if you're utilizing a 5 megahertz transducer, it probably has a useful frequency somewhere between 2 megahertz up to as high as 8 megahertz. So our transducers have multiple frequencies available to them, and we call this the bandwidth. The quality factor is a unitless number that's inversely related to the bandwidth, and so if we have and it's defined as, the quality factor is defined as the center frequency divided by the bandwidth. And so the wider your bandwidth is, the more frequencies in your bandwidth, the lower the quality factor will become. All imaging probes are low quality, or low Q factor. And that means that they have wide bandwidths. There's another term sometimes associated with transducers known as the fractional bandwidth. And the fractional bandwidth is just simply the reciprocal of the quality factor. So you can take your quality factor and just take a reciprocal, getting you the fractional bandwidth, or you can also just reverse the numerator and denominator of your quality factor so that you have bandwidth over center frequency, and that will give you your fractional bandwidth. So imaging transducers have a short pulse, a very short spatial pulse length. They utilize backing material to limit ringing, which reduces the sensitivity of them to echoes. They have a wide bandwidth. They're known as broadband transducers, which implies a low Q factor. And these also have very good axial resolution. Non-imaging transducers, or ones that we just use, say, for Doppler, are either continuous wave or have long duration pulses. They don't require a backing material, which means they can be much more sensitive to the echo strength. They have a narrow bandwidth. They utilize a high Q factor, but they cannot create a good image. If you can remember that imaging is a low Q, then it's easy to remember that quality factor is to think about your general imaging probe. So if it's around 4 megahertz, then the spectrum of the diagnostic ultrasound is 2 to 20 megahertz. Or that would imply if we could utilize the entire ultrasound spectrum, that would be 18 megahertz. So a perfect probe would be able to use that entire spectrum, and you'd get 4 divided by 18, which is a very small number, about 0.22. And so your fractional bandwidth, so your quality factor would be 0.22 if you could use the entire bandwidth, and your fractional bandwidth would just be the reciprocal of that, or 4.5. So hopefully that's a way to remember that imaging probes are low Q, and that since we typically image around 4 megahertz, you can quickly do the math and go, okay, low Q will be 4 divided by some number bigger than 4, and in this case the range of diagnostic ultrasound is 2 to 20 megahertz, and so that gives you a very low Q, and that's a good way to remember what the quality factor is. And then of course the fractional bandwidth is just simply the reciprocal of that. Piezoelectric materials that we use are created utilizing a process known as polarization. And polarization, the polarization process is just applying a voltage across the material during the manufacture in order to align the various domains within the crystal itself, so that instead of having randomly aligned material, we have this nicely aligned material. So the term polarization is a manufacturing technique that allows for better crystal manufacturing. The crystals are much more sensitive because of polarization. Another term that we have to know for piezoelectric materials is the Curie temperature. And the Curie temperature is a temperature at which the piezoelectric material will lose all of its piezoelectric properties. And if it loses its piezoelectric properties, it can never gain them back. So any piezoelectric material raised above its Curie temperature will completely and forever lose its ability to be a piezoelectric. Let's look at what makes the transducer frequency. In continuous wave transducers, those used in Doppler, and these are specifically the Doppler continuous wave transducers, not the typical pulse wave Doppler, but continuous wave Doppler transducers, the frequency is determined by the signal sent to the transducer by the transmitter. So whatever the transmitter is sending the signal at, that is going to be the acoustic frequency. So the electrical frequency equals to the acoustic frequency. Now let's talk about very differently pulse wave transducers, the ones that we use for imaging and for most of the Doppler work we do if we can have a duplex image on the screen. Pulse wave transducers utilize a short electrical spike which is sent to the piezoelectric crystal, which then causes the crystal to vibrate. The frequency of that vibration depends on both the speed of sound in the piezoelectric material and the thickness of the piezoelectric material. Now, we already said that the thickness has to be 1/2 of the wavelength, so that tells you that we can make it different frequency by changing the thickness. Okay, so the thicker the material, since thickness is in the denominator of this equation here, the thicker it is, the lower frequency we're going to have. The faster the speed of sound in the material, the higher the frequency we're going to have. So the frequency of the sound depends on both the speed of sound in the piezoelectric material and that thickness of the piezo material. Faster speed equals higher frequency. Slower speed equals lower frequency. Thinner PZT equals higher frequency, and thicker PZT equals lower frequency. Taking care of our probes is very important and has become so important that it is now part of the ARDMS exam. You have to know that you cannot sterilize ultrasound probes directly. Sterilization is the destruction of all microbes and their spores by exposure to extreme heat, chemical agents, or radiation. If you expose a ultrasound probe to those kind of conditions, you will destroy the probe. What we utilize in ultrasound is disinfection. Disinfection is the application of chemical agents to reduce or eliminate infectious organisms. Disinfection will significantly reduce the microbial load. Ultrasound probes cannot be sterilized. They will break. Usually when they break, the adhesives that hold them together come apart and no longer work. Ultrasound probes must be disinfected. Here is an early ultrasound probe. I'm sure they're having a fun time cleaning that one when they're done. All right, let's talk about the sound beam that comes out of the ultrasound probe. All right, so the sound beams, we're going to make some assumptions for this section. One of our assumptions is that the sound is going to be made from a single crystal element. And then we're going to assume that that element is a round disc-shaped, unfocused PZT crystal. Okay, when I say unfocused, I mean it just has simply a flat surface instead of being curved. When we utilize a crystal such as this, we get a sound beam that comes off of it, focuses it down to the focal point, and then diverges out beyond that. So in our shape of our sound beam, we have some things we need to know about. The focus, which is the location where the beam will be the narrowest, and the focus is always going to be 1/2 of the original diameter of the crystal. So if we're using a round crystal, then our focus is going to be 1/2 of that width across the face of the crystal. The near zone is the area between the crystal and the focus. We call that the near zone because in the near zone, the beam undergoes what are known as Fresnel effects or near field effects and focus down to our focal point. In the near field, there are near field effects that were discovered by Fresnel, and this is what causes the focus to occur. So there's a narrowing of the beam in the near field. The distance from the crystal to the focus is known as the focal length, or the near zone length, NZL if you will. It is just simply however much distance is required to get to the focus. Beyond the focus, there's an area we call the far zone where divergence takes place, and the far zone is known as the far field, the Fraunhofer zone, or the divergence zone. This is where beam divergence occurs. So the focus is 1/2 of the crystal diameter at twice the near zone length, so twice the length between the crystal and the focus, which would bring us out to a point in the far field. It turns out that exactly that point, that the beam is equal to the size of the crystal. So all that implies is that the beam is symmetrical. Beyond the two near zone lengths, the beam continues to diverge and become wider and wider. There is an area around the focus known as the focal zone, and the focal zone is defined as beginning where the beam strength is 1/2 the intensity of the maximum strength. So the maximum intensity for ARDMS purposes is at the focus. The focal zone begins at a point where that intensity is 1/2 of the intensity at the focus, and it ends where the intensity is again 1/2 of the intensity at the focus. So the focal zone is an area between the half the maximum intensity to 1/2 the maximum intensity. This is considered the good area for imaging. When a sound beam emits from a crystal, the beam progressively gets narrower until it reaches the focus. That's known as the Fresnel zone or the near zone. Then it reaches the focus, and the focus is 1/2 the original crystal diameter, and the focus is considered the end of the near zone. The distance to the focus is the near zone length. The focus marks the beginning of the divergence, and at twice the near zone length, the beam is the same diameter as the crystal again. So the beam continues to diverge to infinity and beyond. So how do we determine our focal length or our near zone length? So the focal depth or focal length or near zone length, or sometimes known as NZL, are generally adjustable, and with early systems they had a fixed focus that was set by the manufacturer. So we're going to discuss that type of focus now. The ones that we utilize today in most of our machines are phased array transducers, and this is a different type of focusing. So we're just going to talk about, again, the single crystal transducer and how we get a fixed focus. The fixed focus is determined by the transducer diameter and the frequency of the sound. Let's look at that in more detail. So the near zone length is proportional to the diameter of the crystal squared. So as we double the diameter of the crystal, the near zone length will go up by 4. If we triple the diameter of the crystal, the near zone length will go up by 9. Focal depth and frequency are directly related, so the near zone length is directly proportional to the frequency. A simple equation to remember this is that the focal depth in millimeters is equal to, or approximately equal to, the diameter of the crystal in millimeters, that diameter squared, times the frequency. And in this case, what we do is we multiply our frequency in megahertz. So if we're using 4 megahertz, we multiply that by our crystal diameter. If it's 2 centimeters, we're going to say it's 20 millimeters, and that will give us our focal depth. A more exact equation for it is the focal depth is equal to the diameter of the crystal squared divided by 4 times the wavelength in millimeters. And so when you utilize this second equation, you can see that the units cancel out correctly and we get a focal depth in millimeters. However, the first equation is much easier to remember, and it also allows us to remember that the focal depth is directly proportional to the frequency. So as we increase our frequency, we would get a deeper focus. But you say, high frequency is used to image superficial structures. How does this work? Well, you use high frequency, but you use a very small, much smaller diameter crystal in order to do it. Small diameters allows us to shift the focus closer to the crystal. Larger diameters push it deeper. So when you utilize a low frequency probe in order to get good penetration, you want a deep focus, and unfortunately the lower your frequency, the shallower your focus is. In order to make that focus deeper, you must make your crystal wider and your beam width thicker, which destroys the resolution in the deep field. But at least we get our sound there. Sound beam divergence is directly related to the crystal diameter and the frequency of the sound. So if you have a very small crystal diameter, the angle of divergence in the far field will be very great. If you have a larger crystal diameter, the angle of divergence is much smaller. Also, if you have a high frequency of your sound, you'll get a small angle of divergence, and if you have a lower frequency of sound, you get a larger angle of divergence. Crystal diameter and beam divergence are inversely related. Small crystal, greater angle of divergence. Large crystal, smaller angle of divergence. Frequency and beam divergence are inversely related also. Low frequency, greater angle of divergence. High frequency, smaller angle of divergence. So high frequency will improve the resolution in the far field. That, by the way, is an SPI exam question. There's a principle known as Huygens principle. And Huygens principle is basically states that when you have small little wavelets, the wavelets, known as Huygens wavelets, create spherical waves and will create diffraction patterns, and these diffraction patterns will add together and form a wavefront. So we have small little waves, or point sources, and then they create wavefronts. Interference of these wavelets can cause near-field effects and beam focusing. So you can see that in this display here, we have many little crystals firing off, creating a beam, and the beam now is moving at an angle. So we're actually steering the beam using this Huygens principle. So Huygens principle will become very important as we learn more about phased array transducers, which is what this is. Huygens discovered his Huygens principle when he was studying the light coming from the planet Saturn. And he deduced that the rings around Saturn were made from small little ice particles that blended together, forming what appeared to be solid rings. So Huygens effect allows us to utilize small crystals and angle the beam direction, change the beam direction based on this effect. Near field effects, as we said, in the near field, the beam focuses down. These are called near field effects. And what happens is there's interference patterns that occur in the near field, and these interference patterns create a focusing of the sound beam into what is essentially one main sound beam at the center of the focus. Here is a question for you that you might want to know. Does attenuation for soft tissue increase or decrease with increased tissue thickness? So, if we are going to image a mouse or a shrew, would we have more attenuation than if we imaged an elephant or a whale? Well, of course, as tissue thickness increases, attenuation also increases, so that you need more sound to image a whale than you do an elephant or a horse, and certainly much more for all of those than you do a small shrew. If you get an opportunity, go to the zoo and try doing ultrasound on their animals. They do lots of ultrasound on animals at the zoo. It's actually quite fun if you get a chance to do it. Axial and lateral resolution. So resolution, these are both known as detail resolutions, axial and lateral. Resolution is the ability to create accurate images. In detail resolution or spatial resolution, it is the ability to discern physical characteristics in each of the three spatial dimensions. Lateral resolution is our side-to-side resolution that is perpendicular to our beam path. Axial resolution is along our beam path or parallel with the beam path. And elevational resolution is the thickness resolution, or as we call it, slice thickness. Axial resolution is the ability to display structures that are close together along the line of propagation. The minimum distance that two structures parallel to the sound beam can produce two distinct echoes is known as the axial resolution, and it is defined by this equation, SPL, spatial pulse length, divided by 2. Axial resolution is measured in units of length, or millimeters, and remember, in spatial resolution or detail resolution, smaller is better. Axial resolution is determined by the spatial pulse length. It's related to the pulse duration, and it depends on both the sound source and the medium, because it depends on both the frequency and the speed of sound of the material. Different synonyms for axial resolution are longitudinal, axial, range resolution, radial resolution, or depth resolution. Sonographers cannot adjust axial resolution. The only way to change it is by increasing your frequency by getting a different probe. Axial resolution is improved by creating short pulses or less ringing when we fire off our crystals. And to do that, of course, we need the backing material. Also, axial resolution is improved by using higher frequency, because each cycle is shorter, and therefore we can have a smaller spatial pulse length. So, different ways of creating better axial resolution. With low frequency, many pulses, we get a very large spatial pulse length. With the same number of pulses, at a higher frequency, we get a much shorter spatial pulse length. And then we can even shorten beyond that by utilizing fewer cycles. Lateral resolution is the ability to distinctly identify structures that are side by side. Lateral resolution is determined by beam width and only beam width. And its synonyms are lateral resolution, transverse resolution, angular resolution, or azimuthal resolution, though we don't see azimuthal or angular resolution very often. Most commonly today, lateral and transverse resolution are the terms used for it. Lateral resolution is best at the focus and is considered good within the focal zone. Anytime reflectors are closer to each other than the beam width will show up on the screen as a single reflection. Things that affect lateral resolution are the aperture or crystal size. Harmonics will also affect lateral resolution because it creates a narrower beam diameter. We'll get into why that is in a little bit. And frequency affects lateral resolution as it extends the length of the near zone and the focal zone. The beam diameter or beam width is equal to the lateral resolution, and it varies with depth. Remember that your axial resolution is always a smaller dimension than your lateral resolution, so we always have better ability to discern things along the path of the ultrasound beam than we do side by side. As I said, focusing is very important for lateral resolution, and so focusing is something we need to discuss. A flat crystal or an unfocused crystal will naturally narrow down to a focus. And this is given by that equation I gave you. Focal depth is equal to the diameter squared times the frequency divided by 6. We call this unfocused ultrasound. If we do anything to change the beam, it's going to cause it to be focused ultrasound. And unfocused ultrasound and focused ultrasound are both very important terms when it comes to bioeffects later. You can have a much higher beam strength with focused beam than you can with unfocused, because with focused beams the energy dissipates quicker. So an unfocused beam has a natural shape to it. A focused beam has a more unnatural shape but diverges quicker in the far field. Focusing gives us the ability to concentrate sound energy into a narrower beam and improve lateral resolution. There are 4 ways of which we do focusing. One is external focusing, where we actually apply a lens over the crystal and focus the beam. The other is called internal focusing, where the crystal itself is carved into a shape which focuses the beam. The most common today is known as phased array focusing, which is electronic focusing, which we can adjust with our machines. And then lastly, there's aperture size, which is also done with phased array transducers. And this is a way of varying the size of the crystal depending on how many elements that you're going to fire off at a given time. So our different focusing techniques, they're going to fall into fixed focusing techniques and electronic focusing techniques. So the fixed focusing techniques are the conventional or mechanical focus. In this case, the focal depth and focal zone are determined in the manufacturing of the probe and cannot be changed. There's external lens focusing, which the acoustic lens is placed in front of the piezoelectric crystal. There is external mirror focusing, which is no longer being used, by the way, where an acoustic mirror reflects and focuses the sound, And so the crystal would fire off facing a mirror, which then focuses the sound. And so we don't use that anymore, and this is becoming very obsolete. And then internal focusing, where the PZT material is curved to concentrate the sound beam. Electronic focusing techniques are ones that require phased array transducers, and there's a couple different ways that we can electronically focus sound beams. We can utilize timing patterns to change the shape of the sound beam due to the timing patterns coming off the crystals, and the other way is to decide how many crystals we want to utilize, which affects the size of the aperture. So the crystal diameter is determined in electronic focusing by both the timing of the phased array steering and with the size of the aperture. Different effects of focusing on sound include in the near field, the beam diameter narrows. The focal point will always move closer to the crystal when it is focused. It will never move farther away than an unfocused beam. The beam diameter beyond the focal zone widens. As I said, it diverges quicker. And therefore, focusing will improve the near zone imaging and degrades the far zone, which actually is good for bioeffects. It allows the diffusion of the sound energy much quicker. When you utilize focusing of the sound beam, the focal zone, the area around the focus, always will be reduced. Elevational resolution is our third spatial resolution or detail resolution that we get concerned about. This is known as the slice thickness. It is measured in a plane perpendicular to the imaging plane, and we don't see it on our screen. It is the area that is the material in front of and behind the screen that makes up the elevational resolution. An assumption is always made that the imaging plane is very, very thin. However, depending on your transducer, this is not always correct. Slice thickness can allow reflections from structures in front of or behind what you're imaging to appear in the image. And this is a false, this gives false information, and so you must be aware of it. On one-dimensional array probes, the manufacturers will utilize a fixed focus technique in order to focus in the elevational plane. On multi-dimensional array probes, such as a 2-dimensional or 1.5-dimensional array probe, it allows some limiting focusing in the elevational plane. Let's discuss how this affects imaging. So with 2-dimensional imaging, we utilize multiple pulses sent out from the transducer side by side to form an image. The sequence can be thought of as a pulse is sent out, echoes are received back to the transducer, and then the data is processed from the first pulse before the next pulse is sent out. And the next pulse is sent out in a slightly different direction. And this happens about 3,000 times each second. The image depends a lot on the transducer characteristics, such as the shape and number of active elements, the redirection of the sound beam that is needed to create the image along each scan line, focusing each sound beam, and the shape of the image itself. And we also need to consider what are the consequences of damage to an active element, a single active element. With a mechanical transducer, one that is the single crystal variety that we discussed, an active element known as the crystal is physically moved into different positions to make scan lines. On the video to the right, you can see me spinning a single element transducer around, and that is what creates the sector shape. Pulses will radiate from this PZT crystal like spokes from a bicycle wheel as it spins. One thing that's important with this is to know that at greater depth, anytime you have a sector image, at greater depths, the gaps between the pulses will increase. With mechanical transducers, beam steering is done as the crystal moves, and this is known as mechanical steering. Beam focusing is fixed. It's set by the manufacturer and we can't change it. Elevational plane focusing in a single round crystal making up the transducer, both lateral and elevational focusing will occur. Now this is very different than phased array transducers. So in single crystal round transducers, you get elevational and lateral focusing. What happens with the mechanical transducer if there's damage to the PZT crystal? The entire image is lost. Mechanical transducers contain many moving parts, are very cheap to make, but are easily broken. Today's transducers are known as linear array transducers. All modern transducers are linear array transducers, and in fact they are known as phased array transducers. They are made from crystal arrays that are aligned, in which you take a large crystal and you cut it into many smaller elements. Each element is connected to its own electrical connection, and during the pulsing of the beamformer or pulsar sends out signals to individual or groups of elements in order to create the pulse. During reception, each crystal produces an electrical signal that returns to the system receiver. Different types of array transducers are linear, in which all elements are aligned in a straight line and is flat, convex or curvilinear, where the elements are arranged around a curved surface, and something known as an annular array probe, in which the elements are arranged in circular rings, and this is an obsolete probe because all the rings had to be moved at the same time, so it was a type of array transducer but also a mechanical transducer. And again, we do not use mechanical transducers anymore. With linear phased array transducers, either a vector or sector type transducer, these will have a small footprint, usually 1 to 2 centimeters in dimension. And if you want to think of the hockey stick probe, if you've ever seen me use that with the machine, that's a linear phased array transducer, which is considered a sector shape or vector shape transducer. These have no moving parts, and the beam is steered and focused using phasing. This will produce a phase shape, and so we see in this little picture the different timing. This crystal fires first, this crystal fires last, and it steers the wavefront sort of off in this direction instead of going straight. And so that's very important for our phased array transducers, is to be able to use Huygens effect to steer at an angle. So electronic steering wavelets, again Huygens wavelets, are formed by small time delays between subcrystals. Wavefronts are created by Huygens principle, and the waves will move perpendicular to their wavefront. This is just like waves at a beach. The waves are moving in towards the beach, and the beach is perpendicular to that direction of movement of the waves. Beam focusing with phasing allows electronically focused control, and now we can utilize focusing to control the depth of our focus, and this can be done by the sonographer. In some cases you can select multiple foci, in which if you do that, then you're sending out multiple beams, each one focused at a different depth. Linear phased array transducers are sector or vector ones. If the crystals are damaged, you'll get some loss of signal. This is very unpredictable. You don't know if it's going to affect the image or not. Because there's many elements within the sector transducer, there's up to 500 in some cases, that may be too small to even detect that some of them are out. In other cases you may see some distortion, in other cases the image may be completely unusable. Phased arrays are always adjustable, steerable, and multi-focus. So how many elements are utilized to create the pulse? Well, that's as many as needed. This is determined by the manufacturer, and the number of elements utilized to create the pulse forms the aperture or the width of the crystal used. How does phasing work? Well, when electrical signals arrive at the elements at the same time, the wavefront would move directly away from the transducer. When electrical signals stimulate elements at a slight time delay between them, the wave will move at an angle to the transducer. So let's look at some of this. With phase steering, the electrical signals arrive at the transducer at different times. Now the length of the line between the transducer and what we call this voltage here is considered a difference in time. And so this one's closer, so it's going to arrive first, propagate outward, and this one will arrive last, and when it begins propagating, this one is already quite a ways out there, forming a wavefront using Huygens principle, which then moves at an angle perpendicular to that wavefront. This is phase steering. Phased focusing, in this case we can fire off the outer two crystal elements first, with these being later because you can see the time delay is longer. This will cause a convex shape to our beam, which then, because it moves perpendicular, it will come in and focus in a narrower spot. So it's very easy to tell what direction the beam is going. If you look at the timing, just form a line across it and draw a line perpendicular to your drawn line. Let me go ahead and draw in a line here for you. Okay, so we have a line here that's going to be across our beam, forming the beam front, and then, as I said, the sound wave will move perpendicular to that, so you just draw another one 90 degrees to it, and that's the direction of the motion of the wave. So we can steer that by changing the timing pattern, creating different directions of our beam. With any time there is wave focusing occurring, you'll see a timing pattern which is curved, somewhat curved. Okay, so you can have both steered, you can have focused, and you can have steered and focused beams. So just look for the different timing patterns. As I said, you can have multiple foci, and when this is done, all that is occurring is different beams are being sent out and focusing at different levels. So to have, in this case, 3 different foci, actually 4. If you look at it, it's focused up here too. So you'd have to have 4 different beams sent out in order to create this multiple foci. There's something called dynamic receive focusing, and this occurs because different parts of the different echoes return to different parts of the transducer at different times. So if I have a transducer element with a little reflector down here, this little reflector can get hit by a sound beam and send back an echo, and it should be somewhat intuitive to you that the echo will return to this point closest to it sooner than it will to one farther away. And so because these echoes return at different times, then the machine can utilize electronic delays to refocus the signals in the transducer, or in the receiver, excuse me. And this is done continuously and it's done at all depths, and honestly it's done by magic if you really want to know how it's done. You don't have to know how it's done, just know that dynamic receive focusing occurs constantly at all depths, and it does not change the frame rate at all. However, if you actually want to know how this occurs, then you can look up this article in the Journal of Diagnostic Medical Sonography by Dr. Kremkow, and it's actually a very good article for understanding the dynamic receive focusing. But as far as the SPI exam goes, it's done by magic, but it's done continuously at all depths, and it does not affect the frame rate. Different types of arrays that we utilize. We've already talked about the linear sequential array or the linear phased array. There's 2 other types of arrays that we use that could be used potentially. One is the linear sequential array. It's an obsolete array that was used in early phased array, not even phased array, excuse me, in early multi-crystal transducers. The ones we're familiar with today, the linear phased array, which we call the vector or sector probes, the curved phased array probes, which are convex curvilinear array probes. I guess I should have on here the linear phased array, which is also a linear probe. It doesn't necessarily make a vector or sector image. And annular array probes, and those are, again, the sequential and the annular are obsolete. Alright, so let's quickly talk about annular array probes. I said these are obsolete, but let's just discuss them. Because they do tend to show up on the SPI exam. These are mechanically steered. They produce a sector-shaped image. They're electronically focused because we have multiple crystals available. All these crystals are round, and because they're round, we have both the elevational plane and the lateral resolution. Both can be focused, and it makes a unique artifact if it is damaged, and that's called a band artifact. So you could just imagine a band of dropout across your image here that occurs when a single crystal is broken. But again, they're obsolete, and hopefully they'll take them off the exam. Linear sequential array probes are these big probes that used to come with machines. They have multiple foci in them, or multiple crystals in them, that allow you to select different size groups of crystals to fire off, but they only go straight, they only form rectangular images, and they are obsolete. A phased array transducer is what we use today. It is really the only transducer you need to know about. But this is a sequential array transducer. This is the type of image it made. If you're seeing that in clinicals, give me a call. I want to go visit that clinical site. This is a phased array transducer. This is the type of image you would see with a phased array transducer. If you're not seeing this type of image in clinicals, then I would be very surprised. So electronic arrays, there's different types. Linear sequential, which I said are obsolete. They have up to 1,000 elements. Curvilinear probes have curved faces. They allow for a wider field of view. Linear phased array probes, they have a small footprint, which gives you a narrow near field of view and a very wide far field of view. There's something called a 1.5 dimensional array probe, which utilizes elements not only along the face of the transducer, such as this linear array here, but also across the face of it, which allows some focusing in the elevational plane. And then there's the two-dimensional phased array probes, which allow full focusing in both the elevational and lateral resolution planes, and allows full acquisition of volumes of information. Crystal damage with phased array probes, as we said, sometimes when you have damaged crystals, the image isn't so bad that you can't use it. This one on the left has multiple damaged crystals. However, it probably could still make a diagnostic image. The one on the right has several damaged crystal elements, and it would not make a diagnostic image because there's obviously some dropout areas that would affect the ability to see the tissues. Convex curvilinear array probes are phased array transducers. The crystal array is arranged along an arch surface, which gives you a narrow near field and a big deep far field. Beam steering is done to some extent, but really most of the beams go straight. So you can't necessarily steer your Doppler image with this type of a probe. Okay, though there is some steering being done, usually we can't steer our Doppler with this. So curvilinear, unsteered Doppler, but there is some electronic beam focusing going on. So the image shape is defined by an arc on the top and the bottom. Vector arrays, same as phased array. Rule of thumb is if it can be steered, it's phased array. If the shape at the top is not identical to the shape at the bottom, it's phased array. If it has color or spectral Doppler, it's phased array. And my own rule of thumb is if you're using it after 1990, it's phased array. Let's talk about some of the vector arrays some of the arrays that we will see. This is a 1.5 dimensional array probe, and this allows us to not only focus in the lateral dimension because we have multiple crystals in the lateral, and we can use both aperture, different numbers of crystals and different sizes of beam, or we can use steering to focus it, but we can also use in the elevational plane timing patterns that will allow some elevational steering too, or focusing too. So this supposedly should give us a better image in the elevational plane. Two-dimensional array probes have multiple elements in both lateral and elevational directions and can achieve full focusing in both lateral and elevational planes. This is an image of a two-dimensional array element with a human hair laying across it. So you can imagine how small the elements are in one of these probes. These are very expensive probes, and I frankly don't have any because I can't afford them. Some more pictures of the two-dimensional array probes. Let's talk about you can utilize these two-dimensional array probes in order to make three-dimensional imaging, because they can acquire information in both the lateral and elevational plane. They can acquire, instead of just a image, it can acquire a volume of information because it can get all of that information, and that allows us to produce what we call three-dimensional or volume scans. A four-dimensional scan is just simply a volume scan in real time, and we utilize a technique known as rendering to make that volume of information appear real on our screens, to appear three-dimensional, excuse me, of course it's real, to appear three-dimensional on our screens. Rendering was developed for the most part by the people at Pixar, and so when you look at this two-dimensional image of a character from the Pixar Toy Story, Woody has features that you would think are three-dimensional. However, Woody is obviously on a two-dimensional screen right now looking at us, and he just appears to be three-dimensional. And rendering is the process that makes this two-dimensional image appear to have depth. When we see that in ultrasound, we can see what appears to be depth on a two-dimensional screen because of rendering. So 3D ultrasound, which is three-dimensional imaging with volume data, which gives depth to our two-dimensional images. And so this is a heart complex of vessels that was rendered in order to be seen as three-dimensional. When we look at it, you can kind of see the fetal aorta right there and fetal ductus coming around. This is a very good image here of the ductus venosum coming into the heart, and you can see it on two-dimensional in this image. And this is our typical fetus that we see with three-dimensional imaging. We see the two-dimensional image, and then we add the rendering to it, and it looks like a three-dimensional structure. And this is obtained because we can get a volume of information both in the plane that we're looking at, the regular plane, and in front of and in back of that plane, and put it together and call it three-dimensional ultrasound. Let's move on to some things that are specific to types of probes that we use. So there's something called a side lobe artifact, and in single element mechanical transducers we can get these side lobe artifacts. You'll see here a artifact coming off to the side of the main beam. When this fires off again, you'll see it coming off right there, and that is energy outside of the normal beam, and it causes degradation in the lateral resolution. In a single element transducer, this is known as a side lobe artifact. In a phased array transducer, or one that we would be using today, this is known as a grating lobe artifact. So this picture here is obviously a grating lobe artifact. This is a curvilinear array transducer firing off and showing us a grating lobe artifact. But they're commonly known as side lobe artifacts if you don't want to get too technical. Unfortunately, the SPI exam does like to get too technical, so know that the side lobe artifacts come from single crystal transducers, and grating lobe artifacts come from multi-element array transducers. There's a technique to reduce the grating lobes, and that's called apodization. And so apodization is a technique where the pulsar produces voltages of different sizes to different crystals. And so, as we have already talked about having timing delays in our voltages, apodization is a changing of the actual size of the voltage as it hits the transducer crystals. So apodization is small variations in voltages between elements that is used to reduce grading lobes. Another technique to reduce grading lobes is called subdicing, and so our elements are cut partially through at different depths, and this will also reduce grading lobes. So these are all the different transducers we've utilized in ultrasound over the years. This is an old Doppler transducer which has two elements. This is the Doppler one over here, and this is the imaging element here. It's kind of a unique transducer. Alright, let's talk about the different display modes. So there's three basic display modes with ultrasound. We have A mode, which is known as amplitude mode, and this is the amplitude mode image. Okay, and remember, amplitude mode is amplitude in the y-axis and time or depth in the x-axis. We utilize the A mode, or the brightness or the strength of the return echoes along the axis, to create the B mode image. So each line of a B mode image consists of the acquisition of one A mode, one line of A mode information to create each line of the B mode image, and then the B mode image is multiple lines across the scan area, forming the image itself. So B mode is brightness mode, or also known as grayscale mode. And then the last is M mode, or motion mode. And so if you took your A mode image and just put it down one portion of your B mode image and left it there and observed how that A mode changed over time, that gives you the M mode, or motion mode. So those are our three basic modes of displaying ultrasound information. So A mode is a single scan line. It appears as a series of spikes where each vertical spike is the amplitude of the echo, and the horizontal is the depth of the echo. Strong echoes create taller spikes, and weak echoes create shorter spikes. B mode is, instead of looking at spikes, we display them as dots of varying brightnesses, and multiple scan lines can then be placed together, forming a single image. There's something we call real-time B mode, and this is what we're all familiar with scanning. And this is where the crystals or the pixels appear on the screen with varying brightness with motion. So the motion is just simply that which occurs while we're holding our probe still. And it's over time, of course. M mode is a single scan line displayed over time. And this is a vertical axis represents the reflector depth, so near field to far field, near field to far field. The horizontal axis is time, so from the beginning to the end of the scan. Together, a single scan line is shown changing with time, and so right along this one axis we get a single scan line changing with time. This can be used in something like a chest wall imaging. This is a chest wall image, and we're seeing the near field, a single scan line changing over time, and of course it doesn't change over time. This is looking through the subcutaneous tissues and then the muscles of the chest wall. And then we get to the lung, and as soon as the lung comes down over the image, then for the time that the lung is blocking out our view, we're seeing this strange, what we call field of ants type view. And then when the lung recedes and we see no longer lung in our image, we get this reverberation artifact. And so these are called A lines on the left here, and these are just reverberation artifacts on the right. And this is being used in chest walls to look at pneumothorax today. Here is a curvilinear array format, again, arced on the top, arced on the bottom, a sharper arc on the top than the bottom, so therefore this is definitely a phased array transducer. This one shows a small baby of probably about 6 weeks, maybe 5. All we see is the yolk sac so far. Here is a curvilinear array format, curved on the top, curved on the bottom. And this is a sector format where we see it coming from a single point, so narrow near field and very wide far field. In this case, this is a cardiac. This is an excellent image format in order to look between ribs, and so that's exactly what they're doing with this. This is a linear image, and you can see portions of it are being steered. So the color is being steered from the top to the bottom, right to left. And so this is what we would call a duplex image, in that we have both a B mode and a color mode on top of each other. So anytime you have two modes on top of each other, we can call it duplex, but that's not the typical use of duplex. Typically, duplex refers to a Doppler tracing of an image that's displayed with spectral Doppler. Aperture is the number of elements used to form the image. It's similar to an f-stop on cameras, so if you look up f-stop on Google, you'll find out what that is. Larger apertures result in sharper focus but less depth of field, and it's not as useful for deep scanning. Smaller aperture has less emphasis on the focus but gives you a greater depth of field. And when I say depth of field in our terms, we would be saying the focal zone area. Okay, so it's similar to an f-stop on cameras, but instead of depth of field, you would replace that term with focal zone. So shorter focal zone, greater focal zone. Small apertures have a narrow single focus. Multiple apertures, you have to send out multiple pulses to get multiple foci. And this is a wide aperture. And you can see that with the small aperture, the focus is actually larger than with the large aperture. And so here is a essentially unfocused ultrasound beam on the left coming out. It focuses down slightly in the near field, and then in the far field it diverges. This is a very focused ultrasound beam on the right, and it comes down and it doesn't focus till it's very, very deep, but then it almost immediately starts diffusing. So large aperture, small aperture, focal zones. A dynamic aperture is a technique used to improve the focus over a greater range of depths. And in this case, the system will utilize multiple elements to transmit pulses and receive reflections. So this is known as a variable aperture or dynamic aperture, and it improves lateral resolution. And that's essentially all you need to know about dynamic aperture. And so with that, I'm tired of talking, so I'm going to go join the kitty here in the hammock and take a break for a while. Thank you for listening.